Okay, good morning, everyone, and welcome back from your reading break. How was it? Nakapagpahinga ba kayo or stress pa rin kahit reading break? So hopefully you had a good time and yeah, you found some time to relax. Kasi alam ko most of you ay maraming pinagdaanan before getting into the reading break. A lot of problem sets I do before the reading break. So yeah, hopefully nakapagpahinga kayo kahit konti and ready for the second semester of the SEM. Ano ba mga pinagagawa niyo ng reading break? Pag niyo sabihin nag-ACADS pa rin kayo, ah. So that's also a good time for you to catch up with some lessons that you might have been lagging behind from. Especially lalo na yung iba, I just learned na overloaded for this semester. Or kung medyo, kasi I also understand some of you are in the first semester of your junior year. And for math and probably also applied math majors, this is the heaviest of all semesters. Kasi sabay yung 111, 155, 174. So usually all math yung semester na to. But I hope you are doing well and ready for the second half of the semester. But just an update, there's a memo from the Office of the Chancellor enjoining faculty members from scheduling deadlines for this week. So, but luckily for us, wala naman tayong due for this week kasi kahapon ay sakop pa rin ng reading break. So, exercise number 4, which is included in module number 7, will be due on Monday, and you will have some time to talk about it with your lab instructors kasi right before midnight pa naman sa Monday yung deadline. And that exercise will cover topics from modules 6 and 7. Oh, by the way, module 7 is now live on Canvas. In-upload ko siya kagabi. So you can take a look at it and download it. You can start doing the exercises at the end of the module para ko konti na lang yung gagawin nyo sa Monday. And also, I hope you already found the graded problem set. I think I finished grading everything over the reading break. So if you had some problems uploading your answers in Canvas and you had to submit your work to me via email, tapos hindi ko pa kayo na-replyan, pakisabihan ako, baka nakalimutan ko. But on my mind, tapos ko nang i-grade yung problem set number 1. So hopefully you had a chance to look over it and let me know if you have questions. And with that, I think you will have a good idea of your standing in the class. If you go to Canvas, punta kayo sa grades, makikita niyo yung relative standing nyo. So that computes your grade based on all the graded materials. Yung mga hindi pa graded ay hindi kasama sa kino-compute ni Canvas. And I think generally the class is in a good standing kasi I think the average for the class is about 86.94% standing, midterm standing. So congratulations guys. Hopefully mataas nyo pa siya, pero that's a good place to be at the middle of the semester. We still have one problem set due, but that would be towards the end of the semester. And probably in the next couple of weeks, I'll start talking about the final project. So parang pumayag yata ako na by group yung final project so you can talk about it with your friends in the class if you want to partner with them. Or kung wala kayong idea kung sino yung makaka-groupmate or makaka-partner, just let me know so I can assign somebody to you. If you want to work alone, that's also fine. Pero yeah, just let me know as well, okay? But we'll do that in the next couple of weeks. So for now, we'll be focused on module number 7. And this is about improving the numerical differentiation formulas that we developed from Module 6. If you remember, 2 weeks ago, we started developing some differentiation formulas. We said there are two ways on how to create numerical differentiation formulas. The first one is if you're given a set of data points and you want to also approximate the derivative over the interval comprised of numbers between the smallest and the largest abscissa in the data points given, pwede nyo gawin ay mag-create ng interpolatory polynomial, right? So if you have a bunch of points, say n plus 1 points, you want to approximate the derivative on any x value within the smallest and the largest x value in the data points, Pwedeng kunin nyo lang yung interpolating polynomial na daraan sa lahat ng data points. And then differentiate it. So makakakuha kayo ng isang polynomial, which is not hard to do. Sabi nga natin, bentahe yun ng paggamit ng interpolatory polynomials or polynomials as interpolating functions kasi madali siyang computan ng derivative. So that would be a good strategy. And from a theoretical point of view, that's also a great way to do numerical differentiation kasi may idea tayo kung ano yung magiging error dun sa derivative. You just need to take the derivative of the error term in interpolation. But there's a little bit of a problem there because if you have a lot of data, so n is very large or n plus 1 is very large, that will give us a degree n interpolating polynomial and the derivative would be degree n minus 1. All right? At sabi natin pag malaki yung degree, posibleng yung value nung polynomial na yon o nung error term. Remember si omega ay may product ng mga x minus exabytes. Kung marami kang exabytes, yung value ng omega ay pwedeng lumaki, which leads to the Runge phenomenon, right? Or which is one of the causes of the Runge phenomenon. So medyo kailangan nating maging maingat sa paggamit ng interpolation as a tool for numerical differentiation kasi posible mag-blow up yung error, especially if you have large number of data points. Now, the alternative strategy we developed in module number 6 is to use finite differences, and that is hinged upon the use of Taylor series expansion. So we will take a look at that later. Isa pang example just to review you with it. Pero the focus of this module will be on these three objectives. Number one, we want to find the optimal step size for a machine implementation of a numerical differentiation formula. Second is devise a way to accelerate the convergence of a numerical differentiation formula. And third, as usual, we want to apply these tools to solve scientific problems. Okay. Um, Here we go. Now, if we will go back to last time, if you remember, we derived the 3-point centered formula of order 2. Sabi natin 3 points yung ginamit kasi supposedly tatlong function values yung gagamitin natin. We want to approximate f of x and we say we want 3 data points to use. So gagamitin natin si f of x tapos centered formula. So ibig sabihin si f of x dapat yung nasa gitna. So we move one step forward and one step backward. Correct? So ang gagamitin nating data points ay f of x minus h, at saka f of x plus h. And the formula that we got from this technique by using the Taylor series expansion, eliminating the derivative, those with unwanted derivatives, and solving for f prime, yielded this formula for f prime, right? So this is the 3-point centered formula of order 2 because we learned that the error term here is minus h squared over 6 times a certain value of the third derivative of f. And then if you look at this error term, it seems that if we make h very, very small, ibig sabihin dapat paganda ng paganda yung approximation, right? We also call it, if we are not tracking down the extra factors, pwede nating sabihin ito ay big O na lang ni h squared. Ibig sabihin, the error term vanishes as fast as how h squared approaches 0. Habang magkasing bilis sila ng pag-zero ni h squared. So theoretically, so this is the theoretical error. So theoretically, as we make h very, very small, the approximation should be better and better because the error term approaches 0, right? It doesn't just approach 0, but it approaches 0 in the same rate as how h squared vanishes. Okay. So and then I think I've shown you a similar process last time. Pero if you will implement this say using Excel, medyo may anomaly tayong mapapansin. So for instance, if I want to use this formula in order to approximate the derivative of e to the x at x equals 0, though madali lang naman siyang computein, di ba? So kung ito si f of x, ang derivative niya lang ay e to the power x pa rin. So ang f prime of 0 would be e to the 0, which is equal to 1. Medyo nonsense yung example, pero this is a good elementary example to show you the intricacies of the numerical process. So, pero in real life, of course, either data points yung given or komplikadong function na mahirap computan ng derivative by hand. Okay? Now, if we will implement this three-point centered formula for order 2 in, say, an Excel spreadsheet to evaluate f prime of 0 using varying step sizes, we'll get this table from, this table 7.1, which summarizes the step size versus the error involved. So if we will use step size 10 to the negative 1, the error is quite good, 1.67 times 10 to the negative 3. So this absolute error is computed as the approximate for the derivative. Sabihin natin siyang yung actual derivative minus yung approximate. Anong bang tawag natin sa approximate? Parang wala tayong pangalan sa approximate, no? Tawagin na lang natin siyang f tilde of 0. So kinuha ko lang yung absolute difference between the actual and the approximate value. If I'm going to use 10 to the minus 2, well, it's the error goes down to 1.67 times 10 to the minus 5. So which is basically as expected. Kasi to I order 10 to the negative 1, we brought the error down to 10 to the minus 2. So nabawasan siya ng factor na 10. Pero remember, ano siya, formula siya of order 2. So ibig sabihin, if we decrease the step size by a power of 10, ibig sabihin yung error ay mababawasan or expectedly ay mababawasan by order 10 to the minus 2, right? Kasi nga yung error ay kasing bilis ni h squared nagva-vanish down to 0. So kung binawasan ko si h, dinivide ko siya by 10, yung effect dun sa error, madidivide siya by 10 squared. So kaya mapapansin nyo, yeah, around the same level, 1.67 times 10 to the negative 5. If I further decrease the step size by another factor of 10, the error also was decreased by a factor of 100. Okay? Kasi nga, 10 squared, yun ang babawas. So parang review na rin to ng rate of convergence. Pwede siyang tingnan na sa rate of convergence with respect to decreases in h. So laging power 2 yung nababawas dun sa absolute error. Okay? And the trend goes on as expected, pero dito sa 10 to the minus 6, medyo nagka-problema na tayo because we didn't see the vanishing of the error at the same rate as big O of h squared. So dito ay hindi na na-meet nung method, nung machine implementation ng method, yung expected theoretical convergence. So ibig sabihin, nagkaroon na tayo ng konting problema dito. And that propagates further if we further decrease the step size. Medyo counterintuitive na to. So for instance, sa 10 to the minus 16 na step size, in-expect ko dapat yung error ay mga 10 to the minus 33 na. Pero lo and behold, what we got here is 44.5% na error. Okay? So ibig sabihin there was something wrong in the machine implementation. I assure you walang problema dun sa formula kasi napakasimple lang namang i-encode nitong formula na to. Pero there was something wrong. There is another external factor that played in the implementation of the numerical differentiation routine because it seems that it underperformed with respect to the theoretical error. And do you guys have an idea saan kaya nanggaling yung error? Sino kaya yung pwede kong sisihin bakit nag-underperform yung method or the convergence or the theoretical convergence was not met? Any volunteers?
Yung machine na po, sir.
Sorry, come again, David?
Yung machine na po ba, sir?
Okay, that's great. Thank you, David. So, dito ay if you will recall what I said, in-implement ko to sa Excel, sa isang spreadsheet. And spreadsheets or anything involving computers are finite machines. They can only handle a finite number of digits for every number. Tapos para sa perform ng arithmetical operations, they always truncate the answers and the inputs as well to some decimal digits. All right? So ibig sabihin, doon natin pwedeng isisi yung underperformance. Kasi in a perfect machine, if we will do everything by hand, dapat ito yung error. Pero hindi yun yung nangyari kasi nga yung Excel na ginamit ko, yung spreadsheet na ginamit ko, limited yung number of decimal digits or yung number ng significant digits na ginagamit sa calculations. So, ibig sabihin, if you want to get the optimal step size, kailangan nating balansehin yung, yung theoretical error at saka yung machine precision. So, nangyayari kasi, theoretically, as h becomes smaller, our error becomes smaller. Yun yung sinasabi ng theoretical error. Pero hindi nga lang yun yung nakaka-apekto dun sa approximation process natin. Tama si David na merong round of errors due to the computing machines that we are using. And we also need to take advantage of that. Bakit siya nangyayari? Kasi habang lumiliit si h, okay, si x plus h at saka si x minus h ay palapit na ng palapit kay x. And then, dahil yung function, o halimbawa, si e to the x ay continuous function, so ibig sabihin, the closer x and x plus h to each other are, ganun din magiging magkalapit yung function values nila. So what we will get is two numbers that are very close to each other divided by a very small number. So 2 times h would be a very small number. And since our machines or our computing device here is finite in nature, posibleng dun sa pagmaminus nung nasa numerator, kukulangin yung decimal digits o yung degree of precision ng machine. Pwedeng sabihin ni Excel, zero lang yung nasa taas. Kasi pag nag-truncate ka, say to 15 decimal digits, nagzi-zero yung numerator. So ibibigay niya lang na value ay zero. And also, as h decreases, yung 2h nagde-decrease. And when we ask machines, usually find it difficult to divide a number by a number very close to zero. Kasi kapag ka napakaliit ng denominator, say zero siya to say to um, to 32 decimal digits, ibig sabihin titingnan niya na lang yan as zero when it performs the arithmetic. So yun, kailangan nating balansehin yung theoretical error. We want h to be small enough to get a good theoretical error, but not too small na magkakos ng errors due to machine precision. Okay? Yun yung titingnan natin in the first part of this module, how to get the balance between these two things. In other words, we want to find the optimal step size. Okay? And how do we do that? Well, we can do so by incorporating machine epsilon into our calculations. So just a bunch of notations before we go with the equations in the module. Yung f of x plus h, i-denote natin by, wait, retrace ko lang yung notations ko. Okay, by the way, yung value na ginagamit ni computer pagko-compute nung f of x plus h, that means after truncation, tinatawag ko siyang y sub 1. So yung f of x plus 2h, yung ginagamit ni machine or ni Excel sa pagko-compute ng f of x plus 2h ay dinonote ko by y sub 2. So si y sub k ay yung machine representation ng function value ni x plus k times h, right? Just for brevity of notation. So itong mga y sub i's, sila yung function values na ginagamit ni computer para kay f of x plus I times h, right? But of course, these are finite in nature kasi pwedeng transcendental number yung f of x plus 2h. Pwede siyang irrational, so kailangan talaga natin siyang i-truncate to some decimal digits. And the part that was truncated will be denoted by e sub 1, e sub 2, until e sub k. Right? So ibig sabihin yung eksaktong value ng f of x plus kh would be y sub k plus e sub k. Y sub k, this is the machine representation of the number. And E sub k is basically the truncation error. Ito yung nawala after mong i-cut yung decimal representation ng number up to the decimal digits na ina-allow ng computing device. By the way, k can be negative. So if you're computing f of x minus h, you can write it as y sub negative 1 plus e sub negative 1. So these are the bunch of notations I used in the preceding equations. So essentially, the computer is not perfectly implementing the method that we prescribe it to do, because instead of using the actual f of x plus kh's in its calculations, hindi niya na consider yung e sub k. Kasi pinuputol niya nga yung decimal digits ni y sub k into some up to some point. Okay? So essentially, what the machine actually computes for is this guy, y sub 1 minus y sub negative 1 all over 2h, instead of the actual formula that we wanted to do, which is f of x plus h minus f of x minus h all over 2h. So ito yung kinocompute niya. Machine representation ng forward function value minus machine representation ng backward function value all over 2h. When in fact, it should be doing this thing. Okay? So if we will compare these two guys, okay, kunin natin yung total error. So the total error will be represented by the actual derivative minus the machine answer or the machine approximation. So it's going to be f prime of x minus the machine estimate, which neglects the e sub i's. Okay. So what will happen here is, what did I do here? Well, dito ay gusto kong i-compare ito dun sa actual theoretical error. So instead of a y1, ibabalik ko siya uh, dun sa actual exact value niya dapat. So instead of a y1, dapat ang kinocompute natin ay y1 plus e1, right? So ito yung eksaktong f of x plus h. Okay? Pero dahil ito ay iba dito sa naunang value, kailangan kong i-subtract back yung e1 over 2h na dinagdag ko to get this expression. All right? The same thing was done for the second term. This is the ideal scenario. This is the exact value of f of x minus h prescribed in our derived formula. But again, what we have in the machine estimate is just y minus 1. So to preserve the equality of this line to this line, kailangan kong i-subtract uli yung e to the negative 1, e sub negative 1 all over 2h. Okay? That's how I got this. And I wanted it in this form. Kahit ito ay equal lang naman dito, I want the error to be expressed in this form para pwede kong i-group yung first two addends here. Kasi pag ginroup ko ito, kung matatandaan nyo, ito yung f prime, the actual value, and this is the actual estimate that we derive from the formula. This is your f of x plus h minus f of x minus h all over 2h. And we know what the difference would be. Na-compute natin yan yung theoretical error. Okay? So yung theoretical error na to is negative h squared, f triple prime of psi all over 6 for some psi between x minus h and x plus h, plus this is the round off error. Okay? So basically, dalawang parts na yung total error natin. This is the theoretical error, which we derive along with the derivation of the formula. And this is the round off error, or this is the error due to truncations performed in the machine implementation of the algorithm or of the method. Okay? And if we do some analysis on it, okay, so ito yung total error. Pag kinuha natin yung limit no total error, as h approaches 0, we will see that this will eventually blow up. Because this guy, as h approaches 0, will go to 0. Because f triple prime of psi is just a constant. Hindi nga lang natin alam yung exactong value niya, pero siya yung pinakamalaking value ni f triple prime over this interval. So this is a constant times h squared. So that numerator will vanish as h goes to 0. And then this guy, e1 minus e sub negative 1, would be bounded by a constant divided by something that goes to 0. So the second term goes to positive infinity as well. Okay. Or actually, to make it more correct, lagyan ko siya ng absolute value bars. Kasi I'm not sure if this will go pala to positive infinity or negative infinity. But the thing is, as h approaches 0, the total error approaches infinity. Okay? And this solves the anomaly na napansin natin. So parang ganito yung process. So nag-derive tayo ng formula. Alam natin yung dapat performance ng method. But when we implement it in a machine, nag-underperform siya. So one purview or one aspect of numerical analysis is to investigate why. And here we have really proven that the underperformance of the method is brought about by the round-off error. Because as h goes to zero, even though the theoretical error should vanish to zero, yung round-off error naman ay nagbo-blow up to positive infinity, therefore making the total error approach positive infinity. Okay? So ito yung nagsasabi sa atin na kung balak nyong i-implement sa using a computer yung method, wag nyong gawing si h napakaliit. Alright? So though you want h to be very small so as to satisfy the theoretical error bound, ayaw mo naman siya maging too small to introduce unwanted round-off error. So again, the promise here is we want to get what is the optimal step size. Ano yung tamang h na hindi ganon kalaki at hindi rin ganon kaliit. Right? And that's what we will do in the next few steps. So let's look at the the total error. So again, the total error is a function of h. And so kung gusto natin tong i-minimize, so we want to minimize e. So remember, in minimization, kunin nyo lang yung derivative, equate nyo sa zero to get the critical numbers, and then the critical numbers will give you either a relative maximum or a relative minimum. Okay? Now, tingnan natin kung ano mangyayari dito. Oh, to make the analysis easier, instead of looking at the or minimizing the total error, let's minimize a bound for the absolute total error. So kunin ko yung absolute value nito. And then let's find a bound for the absolute value, okay, or for the absolute error. Now this guy, the first term, could be bounded by h squared times m all over 6, where m is an upper bound for f triple prime of psi all over 6 or for its absolute value. So kung alam niyo yung function f, kunin niyo yung f triple prime, tingnan niyo ano yung possible maximum value niya. Okay? Pwede nating palitan yung f triple prime doon sa error formula by a bound. Tapos yung makukuha ko dito, hindi na siya yung error term, siya na yung error bound. We know that the error will not exceed this value. Okay? And then the idea here is, okay, so that takes care of the theoretical error bound. Now the round-off error bound, si E1 at saka si E2, or si E1 saka si E sub negative 1, hindi natin alam yung exactong values nila. Pero usually this is machine dependent. For instance, in Excel, I think the round-off error is 10 to the negative 15. Ibig sabihin, 15 decimal digits lang yung ina-accommodate ni Excel sa calculations. Pero the thing here is they are bounded by some constant values that depend on your computing device. So the absolute value of E1 will be bounded by, say, the machine precision. Let's call it epsilon. And E sub negative 1 is also bounded by the same value. So basically, E1 minus E sub negative 1 is bounded above by twice epsilon, where epsilon again is a value that depends on your computing device. And then all over 2h, let's keep that. So instead of minimizing the actual error, i-minimize natin yung error bound. Kasi pag nakuha natin yung pinakamaliit na error bound, ibig sabihin napaliit din natin yung error. Right? Now, we prefer to do it this way, not just kasi mas simple siya. Kasi there's no way we can minimize this kasi hindi natin alam yung actual value ni f triple prime of psi. Alam lang natin yung maximum value niya. Pero hindi natin alam kung ano yung eksaktong value niya. Right? So this would be the theoretical error. This is the total error bound. So kunin natin yung minimum nito. Again, this could be minimized by taking the derivative. Tawagin siguro natin itong b of h para sa error bound, which is dependent on h, and we want to minimize b with respect to h. So kunin ko yung derivative ni b with respect to h. Siya ay magiging hm all over 3. This guy will just be epsilon over h. So its derivative would be minus epsilon over h squared. And again, we want to find the critical numbers, so we will equate the derivative to 0, okay? And if we do so, we'll get hm over 3 equals epsilon over h squared. Cross multiplication will give us h cubed equals, or h cubed m equals 3 epsilon. That means h cubed is 3 epsilon over m. So implying that h should be chosen to be equal to plus or minus, not plus or minus, but just the cube root of 3 epsilon over m. Okay? And that's how I got this value over there. Okay? So kinuha ko lang kung ano yung magpapa-minimize doon sa error function. Okay? Any questions so far with that? Medyo hinapo ako ng slide doon. Masyado bang mabilis or okay lang? React naman kayo, guys.
Feel ko okay lang naman po, sir.
Okay, thank you, David. How about the others? Okay, thank you, Ezekiel. Gagawin nyo to sa lab exercise, so I hope the process is clear, okay? Now, all right. So halimbawa, alam mo yung machine epsilon dun sa machine, or alam mo yung ilang significant digits yung ina-accommodate ng computing machine mo. So for instance, in Excel, 10 to the minus 15 yung epsilon niya. So that means I can replace the e here or the epsilon here by 10 to the 10 to the minus 15. And then si m ay yung value ng f triple prime of psi. Pero remember si f of x natin dito ay e to the x. So yung third derivative niya ay sarili pa rin niya. Alright? And then kailangan ko makuha ano yung maximum value ni f triple prime psi, where psi is a number between x minus h and x plus h. But remember, the idea here is h will be very, very small. Okay? Maliit si h. Not very, very, pero small enough. So kung si h ay maliit, so ibig sabihin yung interval x minus h until x plus h ay maliit lang din. So ibig sabihin yung mga values, yung value ni psi ay malapit lamang sa value ni 0. Kasi si 0 yung x natin. We're computing for f prime of 0. So then psi will be a number between negative h and positive h. And when h is very small, then that means that interval is very small. At dahil napakaliit niya, tapos si e to the x ay continuous, so ibig sabihin si f of 0 could serve as an approximate to the maximum value of f triple prime over the interval x minus h to x plus h. So may typo dito. Okay, that should be x minus h to x plus 2h. So basically, I think that's what I wrote in the footnote. Na. So supposedly, kukunin ko yung maximum ni e to the x over the interval x plus h and x minus h. Pero ang idea nga, hindi natin alam si h. Hindi ko alam kung ano yung magpapa-maximum sa kanya. Though the maximum value of e to the x will be attained at e to the x plus h. Pero h is very small. So that means e to the h, which would be the maximum value, will be very close to e to the 0. So I can approximate m by e to the 0. So this would be a good estimate for e to the h, or e to the 0 plus h, which is the maximum of the third derivative. So that's why here I replaced m by simply 1. Again, ang komplikasyon lang doon, yung maximum kasi ni e to the x ay e to the x plus h, and then si x natin dito ay 0. So ang maximum value niya ay e to the 0 kasi increasing yung e to the x. Pero hindi nga natin alam kung ano yung value ni h. We just know that h is very, very small. So h is something close to 0. And e to the x is a continuous function. So e to the h, when h is small, is very close to e to the 0. So, and e to the 0 is equal to 1. And if we calculate this value, it seems that the optimal step size is about, what is this? 1.44 times 10 to the 1, 2, 3, 4, 5. Tama ba? 4 zeros after the decimal point, followed by 1442294 Okay. Now, any questions before I shift to Excel para i-illustrate itong process na to? Okay. If none, then let me share my Excel screen. Okay, let me just share everything. Okay. Okay. Now, ginugol ko pala kanina itong machine precision ni Excel. And from the Microsoft page, it looks like that ang machine precision niya ay nasa na nga yan? Yeah, the number of digits of precision is 15. So Excel stored 15 significant digits of precision. So kaya ginamit ko ay 10 to the minus 15 para dun sa epsilon. Okay. Now, if I go to Excel, okay. So i-reconstruct natin yung table kanina. Nagsimula ako sa 10 to the minus 1. Tapos, kinompute ko yung forward formula. So, meron akong e to the 0 plus h minus e to the 0 minus h all over 2 times h. Remember, ito yung formula na na-derive natin. Oops, what happened? Typo daw. Ha. Saan ako nagkamali ng minus, okay. Dapat doon yung parentheses. And then this guy should be gone. There. So be careful with parentheses. Oh, by the way, clear pa ba yung Excel screen ko or masyadong maliit? Palaking ko kaya. Okay. I hope it's better.
Yan.
Okay. And then kunin ko yung absolute error. Remember the exact value is 1. So yan. Tapos i-plot natin dito sa chart na ito yung yung absolute error. Parehas lang naman in this case yung absolute saka yung relative error kasi parehas lang naman sila. Para makuha yung relative error, i-divide natin by the actual value which is equal to 1 yung absolute error. Okay? Then again, paano pag dinivide natin by 10 yung previous step size? So maging 0.001 na siya. I'll just drag this formulas for f prime and the error value. So you see that from 10 to the, or from order 10 to the minus 3, bumagsak to order 10 to the minus 5 yung error, which is expected because this formula is of order 2. So gada bawas ng power ni 10, yung error na babawasan by power of 100 or by factor of 100. If you continue this process, hanggang 10 to the minus 16, ito yung nasa vortex. So makikita nyo na yung error talaga is about 44%. At makikita nyo dito sa chart na to yung paglobo ng total error. Okay? Which is again contrary to what we expect from the theoretical error. And then we computed the optimal step size. We said that the optimal step size is around kunin ko yung value ng h dun sa vortex. Oh, by the way, before doing that, maybe I can further bring this down. Tingnan nyo sa 10 to the minus 17. Pag 10 to the minus 17 na yung ginamit ko na step size, yung nako-compute niya na f prime of 0 ay equal na kay 0. Bakit kaya ito nangyari? Bakit nag-0 all of a sudden yung approximate para kay f prime? Any idea or any guess why?
Sir, na pinakita niyo po kanina yung sa significant digits. And di ba parang after around 15 ba yan, sir? Parang tinatruncate na niya.
Right, exactly. So, who's that? David ulit? Yeah,
Apo,
thank
sir.
you. Thank you, David. Yeah, probably that's the reason why. Because remember yung formula natin, if you go back to the error to the actual formula in this in the taskbar, it's e to the x plus h minus e to the negative h. All right. So posible dahil si Excel nakikip lang siya ng 15 decimal digits, yung step size na 10 to the negative 17 resulted to the the numerator to become two exact values. So kinompute niya yung e to the 10 to the minus 17 at saka yung e to the negative 10 to the minus 17, and the result after the machine process of truncating the results of the calculations, posibleng equal values yung nakuha niya dun sa numerator. So value minus the same value will become 0 divided by 2 times 10 to the minus 17. Excel will give, that's why Excel gave us the value of 0. Kasi yung numerator upon Excel's calculation, after rounding off to the 15th decimal digits, parehas sila. So nag-0 yung numerator. Okay? So that's why the error here, or nakita nyo na really, decreasing h will not lead us anywhere. So liliit ng liliit yung values na to. Okay? But let's try. Ano yung, kung babalikan natin dun sa handout or dun sa module, yung optimal step size na nakuha natin is approximately 0.00001442249,570. Right? So yan yung na-compute natin using Math36 techniques. Math36 techniques. So hit enter, and you will see na ito yung error. So nakuha natin ay 3.8 times 10 to the negative 11, which is basically smaller than all the previous values. Actually, hindi pala smaller, no? Meron pa tayong 2.7 times 10 to the negative 11, but that is pretty close. And remember, approximate optimal step size lang natin to kasi remember, hindi natin na factor in yung minimum value ng e to the ano yung hindi natin na-factor in doon? Hindi natin na-factor in yung eksaktong value ni f triple prime of psi. Remember, dapat dun sa calculation ay dun sa total error, meron tayong f triple prime of psi. And we just replace f triple prime of psi by a crude approximation. Pinaltan ko lang siya ng 1. Tapos yung 1 nga na yon ay hindi siya yung actual value kasi dependent din nga pala siya kay h. Dapat yung m, pinaltan ko by e to the negative, e to the positive h. Tapos finactor in ko siya dapat doon sa pagde-differentiate. But that will result to a more complicated process, right? But the crude approximation that we introduced gave us a nice idea of what the optimal step size would be, or kung saan siya malapit. And you'll see that it's not that bad kasi it's the second best sumunod dun sa what is this? 10 to the minus 5 or 10 to the minus 6. And then if we further fish around that neighborhood, we see that if we divide that computed approximate optimal step size, mas may improve pa natin yung approximation. So we get 4.2 times 10 to the minus 12. But maybe it's a misnomer to call that the optimal step size because we replaced f triple prime of psi by a crude approximation. Okay? Pero yun nga, it's not that bad at all. Kahit crude yung approximation, madali nating na-compute yung optimal value of h or yung near optimal value ni h without resulting to much complicated analysis. But here, we indeed got a good idea kung hanggang saan lang dapat yung gagamitan natin or around what neighborhood yung gagamitan nating value ni h. Okay? Does that make sense, class? I hope it does. Okay, let me go back. And balikan ko tong module. Okay, any questions before I proceed? Mukhang ganito na
Sir,
kayo, no? Yes, David.
Question po kanina, nung pinakita
Aha,
niyo pala sa amin about dun sa yung sa website po ng Microsoft about Excel,
aha,
sabi po niya 'di ba around 15 significant digits?
aha, yes.
Pero kung ma-consider ba natin na significant digits kasi po yung nilalagay natin kanina is na H is like 1 point kasi po sir 1.000 ba siya nun, hindi siya 0.000 kaya nag-umpisa na agad yung pagbibilang natin ng SF?
Yes.
Okey po.
Medyo
Ah,
komplikado yung, medyo di pala, medyo technical yung significant digits. May mga rules pa yon. Ilan yung zeros, yung mga zeros sa unahan, zeros before. Pero ang idea kasi ay nino-normalize ng machines yan. So laging ang format nila ay 0 point, decimal 1,
okay.
decimal 2, and so on, times 10 to some value. Ito yung
Yun po.
tinatawag na IEEE standard. So almost all
Opo ata.
computers follow the IEEE standard. So talagang 15 decimal digits. So ibig sabihin 10 to the minus 15 talaga. Kasi lagi muna
Opo.
nating sina-scientific notation. Pero binary minsan yung ginagamit. So minsan ito ay times 2 to the exponent, kung ano man yung exponent na kailangan. Okay. Depende dun sa numeration base. So if you want to get the best, really, the best or the optimal step size, kailangan pag-aralan din yung machine. Ano yung, kung ginagamit niya ba ay binary, kung decimal ba, or hexadecimal, or base 16 yung ginagamit niya, magpa-factor in pa rin yun sa pagbibilang ng significant digits. Tapos sabi ko nga kanina, dito pala ay dahil crude estimate yung ginamit natin, dapat pala to si M. Pinaltan natin by e to the h. Kasi ito yung maximum talaga ng f triple prime of psi all over e to the minus h. Pero ito ay, so pwedeng ito yung inoptimize ko with respect to h. Pero magpa-product rule na ako dito. Gusto kong takasan yung komplikadong pag-solve. Kasi pag ito yung ginamit kong total error bound, dinifferentiate ko to, pag inequate ko kay zero, mukhang transcendental yung makukuha kong equation. At baka mahirap siyang i-compute. Nasa math 175 pa yung methods how to compute the roots of a transcendental function. Yes, Lian? Lian Grace?
Sir, so does that mean po na iba-iba po yung makukuha naming optimal step size?
Posibleng iba-iba. Kasi pwede niyong palitan si M by or pwedeng palitan si F triple prime by uh, by some values. Pwedeng crude approximation siya, pwedeng conservative yung bound for M na piliin nyo kasi si M kahit anong number na mas malaki dun sa F triple prime. So kung wala ka masyadong idea kung ano yung maximum value, so halimbawa cosine x. So kung yung third derivative ni cosine, alam natin maglalaro lang siya hanggang kay 1. Pero nakadepende pa rin siya dun sa interval na x plus h at saka x minus h. So pwede mong piliin saan nga ba malapit yung cosine dun sa interval na yon. Or if you want to be pessimistic with the error bound, pwede mong palitan si m simply by 1 kasi alam mo sa kahit anong interval, yung maximum ni cosine ay equal lang kay 1. So, posibleng magkakaiba yung error bound na makuha nyo, depende dun sa yung optimal step size, depende dun sa gagamitin yung approximate kay m or gagamitin yung value ni m. Pero dapat may basis kayo kung bakit yun yung ginamit nyo na m. Right? Tapos, isa pang posibleng dahilan kung bakit iba-iba kayo ng optimal step size ay baka kasi iba-ibang machines yung gagamitin nyo. So halimbawa, ang gagamitin nyo lang ay yung pantindahang calculator, kakaunti yung decimal significant digits na ginagamit niya. So posibleng iba yung optimal step size na makuha nyo kasi the optimal step size depends on the machine epsilon or the machine precision. So kung gagamit kayo ng MATLAB, you can ask MATLAB to use higher precision. Pwedeng utusan nyo si MATLAB na I think the default kay MATLAB ay 15 decimal digits din. Pwede nyo siyang utusan, wag taasan mo yung significant digits, gawin mo nga 32 decimal digits yung i-consider. You can do that, but of course, yung total error ay bababa. Okay? You can find the best, really a better uh, h than what we got here, pero that will come at a cost na medyo mabagal or mas mahaba yung computation na gagawin ni MATLAB kasi mas marami siyang digits na i-consider. So yun yung mga dynamics ng numerical analysis on how to get a better formula. Okay.
Thank you po, sir.
All right, you're welcome. Now, wala na akong time to discuss example 7.1, but I'll just put it down as a reading assignment. I discussed yung detail kung paano siya ginawa. So, pwede niyo siyang sundan. So, yung first part naman ay review nung ginawa sa module 6. And then, finorm lang yung total error. Okay? Ito yung theoretical error. Ito yung galing na kuhang error mula dun sa truncation. Okay? Siguro I'll say a few words why we got 40E over 6H here. Or I think this should have been epsilon, not E. Okay? So, kasi kukunin natin yung absolute value or kukuha tayo ng bound para dun sa absolute value. So, itong guy na to, pag kinuha niyo yung absolute value niya, tapos ginamit niyo repetitively yung triangle inequality, makukuha niyo na siya ay mas maliit sa 2 epsilon plus 9 epsilon minus 18 epsilon plus 11 machine epsilon all over 6h. Plus 18 pala yan. Okay? Triangle inequality plus yung bawat isang truncation error ay bounded by the machine precision epsilon. Okay? So that's going to be 2 plus 9, 11 plus... Tama ba? Parang kulang. 29, 38, 40. Tama pala. So 40 epsilon talaga. Kaya nakuha yung 40 epsilon all over 6h. Kasi ito yung sinasabi ko kanina when I explained something to Lee and Grace. Ang pinapakunan dito ng derivative ay si sin x. So si sin x, ang third derivative niya ay sin, cosine, sin, cosine. Ay cosine. Tapos, supposedly siya ay cosine ng psi mula kay x minus 3h, x. Pero ang problema ngayon ay hindi binigay ba yung value ni h? Yeah. We want to approximate the derivative at x equals 0. So essentially, what we will compute here is the maximum value of the absolute value of cosine x, where x is between negative 3h and 0. So dito ko lang ima-maximize yung cosine o yung absolute value ni cosine from negative 3h to 0. Pero the idea here is kung ayoko ng pag-isipan pa ng mas malalim, ano yung maximum value ni cosine over this very specific interval, I could be pessimistic about it and say, alam ko ang maximum value ni cosine ay laging 1 over any interval. So I can choose 1 to be a replacement for f, not f triple prime, but for the fourth derivative pala of f over this interval. Okay. So that means here, kaya itong maximum na to, yung m na ginamit ko ay 1, kaya natira na lang si h cube over 4 dito. Yung epsilon na ginamit ay 10 to the minus 5 kasi dun sa problem, inassume na ang machine precision ay 10 to the negative 5 lamang. So ito yung parang pantindahang calculator lang. 5 significant digits lang yung ini-store ng ating calculator dito. Okay? Now, parang paulit-ulit kong sinabing third derivative nung sign. Pero iba na pala yung formula dito. Theoretical, ito yung 4-point backward formula. Tapos na-compute na yung relative error ay yung theoretical error ay order 3. Tapos ang involved ay fourth derivative ni f. So anong fourth derivative ng sine? First derivative ng sine ay cosine, then sine, cosine, sine. Tama ba? Fourth derivative niya dapat ay sine. Babalik, no? Dapat 4. So, dapat ito pala ay sine. Tama ba, guys? Fourth derivative. Nabobo ako sa pagde-differentiate.
Tama po ata, sir.
Yeah. Siguro nung sinulat ko tong vortex, nasa isip ko ay third derivative din. nung illustration. Pero dito sa example, fourth derivative pala yung involved sa error. So yung sign value. So and then this, you will see that this is much more pessimistic. Kasi yung maximum value, yung fourth derivative at psi, ay ine-evaluate lamang natin or minamaximize natin from negative 3h to 0. Pero what's the idea there? Sa interval na to, habang si h ay paliit ng paliit, yung value ni sine ay palapit ng palapit kay 0. Tama? Kasi ang sine ng 0 ay 0, sine is continuous, so the closer h becomes with respect to 0, etong value na to, ang sine ng negative 3h ay palapit din ng palapit kay 0. Pero hindi ko alam kung ano yung posibleng pinakamalaking value ni absolute value of sine x. So, kaya ginawa ko, naging pessimistic na lang ako. I erred on the conservative side na alam ko naman yung sine ay laging mas maliit sa 1. So, kaya pessimistic dito yung error bound. So, yeah, that's why here medyo yung makukuha nating h is around this value. Okay? Pero if you replace the fourth derivative of psi by a number, say square root of 2 over 2, kasi sure ka naman na yung uh, yung 3h ay mukhang hindi naman lalampas ng pi over 4. So, ibig sabihin, nandun ka lang sa interval na yon, ang maximum lang ni sine is square root of 2 over 2. You can also do that as long as you can justify that really the value of the fourth derivative for small enough h will not exceed square root of 2 over 2. Then you can do so. You might get a bigger value for h, right? Or a better value for h. So yun, posible talaga magkaiba-iba yung step size. Depende kung ano yung pangpapalit natin sa fourth derivative. But as long as you replace it by a reasonable value, then that is fine. All right? Any other questions? Wala na? So next time, we'll be talking about another method on how to improve the numerical differentiation formula. Pero ang mas concern naman niya ay yung rate of convergence at hindi yung accuracy or optimal step size. All right? And then, oh, by the way, binasa ko pala yung mga comments nyo dun sa problem 1 ng problem set. And I still find, I realized that some of you are still having some troubles with programming. And I don't want programming to hinder us or hinder you with your progression in Math 174. So maybe I can offer a tutorial session for MATLAB, especially if you guys also, not just for Math 174, but if you are interested in using MATLAB in the future, probably say in your SP or in your thesis, maybe it would be a good idea to meet about MATLAB at matutunan yung basics niya. So if you guys are interested, I can lend you some of my time and we can discuss the basics of programming in MATLAB and how to take advantage of this nice computing app that UP provides us for free. So sabihan nyo lang ako probably kung game kayo to do a MATLAB tutorial or a MATLAB clinic session. So you can talk with it among yourselves and then just let me know, because if I could get, say, at least siguro 5 students that are interested, then maybe I can open up a tutorial session. So yeah, kailangan ko lang ng magka-idea kung may mga interesado bang umattend para makapag-prepare ako so I can offer it. It might be a little late for Math 174, pero siguro for other purposes it might be good. So it's never late pa naman. Kalahati pa naman yung SEM ang meron tayo sa Math 174. So if somebody can take charge and summarize the names of those who would be interested, it would be well appreciated. And if you can let me know by the end of the week, then we can schedule something. I can prepare next week, and then we can have it 2 weeks from now. Okay? And then we can make it a regular thing. Simula sa basics, kung gusto niyo pa rin magpatuloy, so we can talk about more advanced programming in MATLAB. Okay? So, if there are no other concerns, then thank you guys for coming today. I really appreciate the questions and the comments. So, I hope you enjoyed the rest of the day, and let's see each other again on Thursday. Bye, everyone.
Bye, sir. Thank you, sir.
Thank you po, sir.
All right, you're welcome.
Thank you po.
Mhm.